Welcome back. We have two talks this afternoon. The first one will be given by Frei, who recently joined Dartmouth College, coming from Rice. He will tell us about symplectic involutions of symplectic fourfolds of symplectic Kummer. Sorry, I have an extra.
That's okay. You can add many symplectics to the name. That's fine. Yeah. Well, thanks so much to the organizers for the invitation to be here. I'm really happy to be here, and thanks everyone for also attending. It's been a great program so far. So yeah, I want to talk about this project. It's joint work with Katrina Honig's, and we were sort of interested in studying these sort of arithmetic properties of these Kummer fourfolds, and that sort of naturally led us to studying symplectic involutions. So let me start by telling you a little bit about the varieties that I'm interested in thinking about. And the first example that I want to talk about is a Kummer K3 surface. So we actually saw these earlier in Daniel's talk. So if I start with an abelian surface, it has this natural involution, which I'll call iota, just sends a point to its negative. And I can take the quotient by that, but then I'm going to get 16 singular points corresponding to the two torsion points of the abelian surface. There are 16 of them. But if I blow up those 16 singularities, then this gives me a K3 surface. Okay? This is called the Kummer K3 surface, and I'll denote it K1 of A. So this is sort of the standard construction for the Kummer K3 surface, but I actually want to talk about a different construction. So I can actually use Hilbert schemes to get the same thing. So Hilb2, this is going to parameterize zero-dimensional length 2 subschemes of A. So generically, this is going to look like two distinct points from A. But when I sort of have a single point, instead of counting it with multiplicity 2, I want to sort of think of it as two separate points that have like collided together into one, and I want to remember that tangent direction in which they collided. Okay, so these are sort of other length 2 subschemes, but they're only supported at a single point. Okay, well, because A is an abelian surface, I can take these length 2 subschemes and sum up the points in their support, and this gives me a map to A. Okay, so if I have two distinct points, I'm just adding them in the abelian surface. If I have a point with a tangent direction, then it maps to 2 times that point. Well, if I look at the pre-image of 0 under this summation map, this is actually exactly the Kummer K3 surface, right? Because I'm going to sort of identify a point with its negative, which is what happened when I quotiented by the involution. And any two torsion point, if I take just that point with a tangent direction, then it's going to sum to 0. So I get sort of this entire P1's worth of points corresponding to sort of having blown up those two torsion points. Okay, well, I can do this for sort of any n instead of just looking at Hilb2. I can think about length n subschemes of A and consider the summation map. And I'll sort of index slightly differently. So if I look at summation from Hilb n plus 1, then I want to think about the pre-image of 0, and I'm going to call that the generalized Kummer variety. Okay, so this is like a very natural sort of generalizing the construction of this Kummer K3 surface. Okay, so over the complex numbers, these are examples of what's called Hyperkahler varieties. There's the definition if you're interested. They come with this sort of non-degenerate holomorphic 2 form. They maybe can be best thought of as sort of higher dimensional generalizations of K3 surfaces. Like we saw that very explicitly with this construction, but they share a lot of the same properties. In fact, every 2-dimensional Hyperkahler variety is a K3 surface. They're sort of important in terms of classifying varieties because they're one of the main building blocks for Kahler varieties with trivial first Chern class. And they come in sort of 4 known deformation families, although we expect there to be even more of them. The definition is very general, but we sort of don't have a lot of different examples of them. So there are ones which are deformation equivalent to Hilb n of a K3 surface. There are ones which are deformation equivalent to the one I've introduced here, the generalized Kummer variety. And those 2 families show up in all even dimensions. Okay, so I guess I didn't say it, but this Kn is 2n dimensional. And then there are 2 sporadic examples due to O'Grady in dimension 6 and 10. And these have been studied a lot over the complex numbers, but if you sort of just take this definition that I've given here, it makes sense over any field, and you can start to ask about the arithmetic properties, and these have been sort of less studied. Okay, so this is what I want to do. I want to sort of start thinking about arithmetic questions about these varieties, and I don't want to just think about the generalized Kummer variety. I want to think about other varieties in that deformation family. Okay, so let me introduce those. To do that, I'm going to take sort of a slightly different perspective of the definition I just gave for the generalized Kummer variety. I want to think about a moduli space of sheaves. Okay, so the points in this space parameterize rank 1 torsion-free sheaves with trivial first Chern class and Euler characteristic the negative of n plus 1. Okay, and in fact, any sheaf like this, you can check that it can be written down as this sort of tensor of an ideal sheaf of a length n plus 1 subscheme with a degree 0 line bundle. Okay, so what this is saying is that this moduli space is isomorphic to Hilb n plus 1 cross pick not of A, or the dual abelian surface, which I'll call A hat. Okay, well, I have a sort of a natural map then, which is that summation map on Hilb n plus 1, and I can just do the identity on A hat. And then I can realize the generalized Kummer variety as the fiber over 0, 0. So this now leads to sort of a way to generalize this perspective by thinking about other moduli spaces of sheaves. Okay, so the notation that I'll use is M of V, where V is some like fixed topological data. Okay, so it'll fix the rank, the first Chern class, and the Euler characteristic. Okay, and then we sort of again have a map, and yeah, I should say I want to assume that this moduli space is a smooth projective variety. You can do that by assuming some sort of mild assumptions on the fixed data V. And then the map I want to consider is slightly different, but I can take the determinant. This is going to take any sheaf and spit out a line bundle. Right? So I can think of that as sort of up to translation, a point of A hat. And then I can take the determinant of this Fourier-Mackay transform of my sheaf, which is sort of a fancy way of taking a sheaf on A and spitting out a sheaf or maybe a complex of sheaves on the dual abelian variety. Okay, so I've written the definition here. You take your sheaf on A, pull it back to the product A cross A hat, tensor with this Poincare bundle, and then push down to A hat. So if that's not something, it's okay if the details are not so clear, but right, this gives me a map from the moduli space to A. Okay, and so what I want to do is consider the fiber over any point of this map. Right, this is like my replacement for that summation map. Okay, and in fact, any fiber, which I'll write K of V, is a smooth projective variety, and it is in this deformation family. So it's deformation equivalent to the generalized Kummer variety for some n. Okay, so not all of the varieties in this deformation family arise in this way, but a lot of them do, and this is a very sort of explicit way to start studying these varieties in this family. And so this is what I'm going to focus on, although I'll restrict a little bit more. Right, these show up in all even dimensions, but I just want to think about fourfolds for now. Okay. Again, if I think about the ones which are two-dimensional, these are just K3 surfaces. So the fourfolds are sort of the first interesting case where new behavior might happen. And it's already sort of complicated and interesting enough in that setting. Okay, so the sort of arithmetic thing that I want to consider is the cohomology. Okay, so let me first sort of tell the story about what happens over the complex numbers, and then we can sort of look at what happens when you generalize to other fields. So this was first studied by Hasse and Schinkel. So they showed that if you start with a Kummer fourfold, so one of these fourfolds deformation equivalent to this generalized Kummer fourfold, then you can look at its middle cohomology, and it sort of breaks into two parts. There's sort of this boring part coming from the lower degree cohomology, and then there's this interesting part, which is 80-dimensional, this vector space V. And what they do is show that it's generated sort of by these classes, which I've called is this how I don't know how I laser. It's okay. Oh. These classes Z tau and Z0, where tau corresponds to a 3 torsion point of A. And what are these classes? These are the cycle classes of a K3 surface living inside of this Kummer fourfold. Okay, so I have this two-dimensional subvariety of X, and you can even think just like singular cohomology or singular homology. Take the fundamental class, and this gives a class in the middle cohomology of X. Okay, great. So where does this come from? Where are these K3s coming from? Well, what you can do for this 3 torsion point, it induces a map on the abelian surface, right? You can translate by a point, okay? And if I compose that with the standard involution, then this composition induces a map on the generalized Kummer variety. Okay? And this map is actually a symplectic involution. And the fixed point locus contains a K3 surface. So that's how I'm sort of, from this 3 torsion point, I'm producing this K3 surface. And in fact, that sort of spans this interesting piece of the cohomology. Okay, you can sort of very explicitly describe this K3 surface. It's not just any old K3 surface, but it happens to be the Kummer K3 surface that we looked at earlier. And that's the story if you're just looking at the generalized Kummer variety. And so to get at these other Kummer fourfolds, Hasse and Schinkel use deformation theory. Okay, so they show that like these involutions and hence the fixed point loci also deform. Okay, so that's the story for complex Kummer fourfolds. And so the natural question is, if I'm working over a non-closed field, right, I can look at the cohomology. This time I'll look at a tall cohomology. But because I have a Galois action on the Kummer fourfold, I get this induced action on the cohomology. And so can we understand this cohomology as a Galois representation? Okay. I think sort of the natural guess, just by looking at what happened here for the generalized Kummer fourfold, is that we should sort of hope that as a representation, this vector space V, the Galois action is determined by the Galois action on the 3 torsion of A. It should sort of permute those K3 surfaces in the same way that it permuted the 3 torsion points. But sort of when you start doing this deformation theory, deformation theory is very coarse compared to the Galois action. And so it's not clear as you start deforming sort of how that action is going to behave. Okay, so the issue really is that sort of if we want to understand the Galois action when we deform, we need to have a description of the involutions as they deform, right? And if we can write down those involutions explicitly, then we can write down their fixed point loci, and we can look at how the Galois group is acting. Okay, so that's sort of the first thing in terms of trying to understand this cohomology. We need to understand these involutions. What I'm going to do is sort of add one more assumption, which is that I want to sort of write this Kummer fourfold is the fiber over some line bundles L and M, and I want to assume they're symmetric, which just means, again, there's the sort of the standard involution. I want it to fix these line bundles. Okay, and so what Katrina and I show is that the corresponding involutions, right, if on the generalized Kummer fourfold you had this sort of translation by a 3 torsion point with the standard involution, what those deform to are of this form. So I again sort of have translation by a 3 torsion point with the standard involution, but then maybe I have to tensor by some degree 0 line bundle. Okay, so X and Y are points in the 3 torsion of A cross A hat. And L sub Y means I'm thinking of my point Y in A hat as A hat is pick naught, so these are degree 0 line bundles, and I take the corresponding degree 0 line bundle. Okay, so I get 81 of these, but they now correspond to this subgroup GA of V inside this 3 torsion. Are there questions so far? Pause for 1 second. Okay, so right, so this subgroup GA of V is sort of dictating what the involutions are. So what is this subgroup? Well, it's a set of solutions to these 2 equations, where phi L is this map from A to the dual, which is sending points to sort of the induced translate the line bundle L by that point and tensor with L inverse. So this spits out a degree 0 line bundle. I think of that as a point in A hat. Similarly for phi M, it goes from A hat to A. Okay, well, like where does that come from? If I take any pair of points in A and A hat, I can always sort of translate and tensor by this degree 0 line bundle, and that's going to be an automorphism of this moduli space. Okay, but I don't want an automorphism of the moduli space. I want an automorphism of the generalized Kummer fourfold. So I need that it restricts to an automorphism on the fibers of this map. And if you sort of write down what does it mean to fix the fibers of this map, these 2 equations exactly fall out. So that's sort of really all that is coming from. And then I want to sort of take these automorphisms and compose them with the standard involution on the abelian surface. And so I need, this is sort of where I use that assumption that L and M are symmetric so that the standard involution also preserves fibers. Okay, so let me sort of do a couple of examples for this subgroup. right? So if I took the sort of topological data 1, 0, minus 3, then this is sort of exactly the data that gave back the generalized Kummer fourfold. So this is sort of the standard case that Hasse and Schinkel were studying. And if you look at the two equations in this setting, well, you can take the generalized Kummer fourfold to be the fiber over the structure sheaves of A and A hat. And you sort of exactly get that the 3 torsion of A is what falls out. Okay, so this subgroup recovers the involutions that Hasse and Schinkel were studying in that case. But you can get other interesting subgroups. So if you sort of change the 3 and the 1 from the example above, then that sort of swaps the roles of the x's and y's, and you get that this group is the 3 torsion of the dual abelian surface. And one more example, if you pick sort of some of this data to be 0, then you're going to get that these isogenies are just the 0 maps, and so you get that this subgroup is the product of the kernels. So really, this is just to say that you really do get sort of lots of different subgroups here. And this group is going to be sort of what controls the cohomology, in fact. So one more piece of notation, which is that I want to sort of take this group, right? It's a subgroup of the 3 torsion, and so it has a natural action of the Galois group on it. And I want to make the permutation representation. So I'm going to make a vector space where the basis is the elements of that group. And the Galois action is exactly sort of given by how it acts on the elements of that group. Okay, and so what we show is that as a Galois representation, this middle cohomology, it again sort of has this boring piece coming from lower degree cohomology, and then it has this 80-dimensional representation, which is the subrepresentation of this permutation representation, which is sort of the direct sum complement to a trivial representation coming from the identity element in the group. And this is really just sort of a translation of what Hasse and Schinkel did. Okay, so right, these involutions again have a fixed point locus which contains a K3 surface, and if you take sort of the appropriate vector space spanned by this difference of the cycle classes, then that spans the rest of the cohomology. But now that we sort of have this explicit description of the fixed point loci, we can actually look at how the Galois group acts. And that's what tells us the Galois action. Okay, and just to sort of reiterate again, if I look at this specific topological data so that I get back the generalized Kummer fourfold, then we exactly sort of recover the Hasse-Schinkel results along with this additional information that we expected, which is that 80-dimensional piece as a Galois representation is being determined by the action of the Galois group on the 3 torsion of A. Okay, and in terms of sort of the story for other Hyperkahler varieties, right, I said that these generalized Kummers are sort of one of the deformation families. And this is already sort of an interesting departure from what happens for one of the other families, which is coming from moduli spaces of sheaves on K3 surfaces, where all of the cohomology is just determined by the cohomology of the K3 surface, okay, and sort of doesn't depend on which topological data you pick. Okay. I started at 3:30. Right. 2 minutes. Okay, great. Okay, so so this sort of has some nice implications in terms of studying the derived category, but maybe I'll skip that to the summary, which is that sort of from this understanding the cohomology, we can show that there's an abelian surface over a number field for which the sort of standard generalized Kummer fourfold is not actually a derived equivalent to the Kummer fourfold for the dual abelian surface. And this is a little bit surprising because we sort of expect that over the complex numbers, these things will be derived equivalent. And so this is saying that sort of, if they are over the complex numbers, sort of whatever is happening at that level doesn't descend to the number field, which is a little bit surprising because it's telling you sort of how this derived equivalence is being made is sort of a somewhat unnatural way. Okay, so thanks, I'll stop there.